Good morning or good afternoon, everyone. Welcome to Calcitech's webinar on how IEEE2030 enables DER integration. I would like to thank you all for taking time from your schedule to attend this webinar. I am Nirmal Thail, working in product management and marketing for Calcitech. A few points to keep in mind before we start out. This will be a listen-only on-demand webinar. However, to facilitate clearing of your doubts or queries that may arise during the course, please feel free to send us your questions on marketing@calcitech.com, or you can type in the questions in the window provided in the GoToWebinar. We will be sharing our response to you over email. Welcome once again. So here is the agenda or topics which will be covered in this session. First, we will explore the background of DER and why DER integration is important. Then we can look at the options for utilities to integrate DER assets and what are the challenges on those. How IEEE2030 helps in achieving this objective. What are the different solutions and features of the solutions which is built on top of IEEE2030 provided by Calcitech. We can also look at a couple of case studies before winding up the sessions. To give background, so deployments of distributed energy resources, that's DER, such as solar plants, battery storage systems, electrical vehicles, wind farms, are progressing on record pace. DER can interlace with main grid gracefully, which helps prosumers to sell excess power while drawing from the main grid as needed. These advances are intended to support a more sustainable, decarbonized energy future. However, decentralizing the electricity grid introduces a whole lot of new instabilities in the grid. For example, if we go with conventional approach, whenever a local fault, a voltage spike, or any other disturbances happen in the grid, a protective circuitry quickly shuts down all the energy sources to isolate the fault. However, this will lead to cascading system-wide instabilities on a system with high intensity of DER. So, it's important for DER plants to automatically ride through these disturbances rather than simply shutting down. Or if you look at the other case, whenever a DER resources is connected or disconnected, it will disturb the grid. Even though these disturbances are feeble, as the number of DER sources increases, the strain on the grid increases exponentially, which will cause devastating effects on the grid, which will ultimately end up in blackout. So what needs to be done by utilities? So DER is supposed to improve the reliability benchmarks without impacting the current resiliency and safety. DER would need to support utilities in maintaining the grid stability by providing grid services. Accurate forecasting and scheduling of variable distributed energy generation is assumed significant importance for load dispatch centers of the utilities. So the operators needs to establish a bi-directional communication link with each DER. However, coordinating with each individual DER became an enormous task for the system operators. At the same time, the time for onboarding a DER, cost of onboarding, and process of integrating the DER into operations and market must be kept low and simple to make sure more stakeholders are onboarded to the system. So, DER must enable grid services, which are like to regulate the voltages throughout the distributed network, to coordinate the protection logics around the network, reverse the power flow, or you control the power flow directions, and avoid unintentional islanding, increased equipment line duty, like improving the system operations life cycles, sustained variability due to weather. So most of the DERs depends upon the renewable sources. So weather has got a huge impact on the generation capacity. So and then the capacity switching of the grid. These are a few of the grid services which should be exposed by the DER. So let's look at the challenges on this. So usage of legacy SCADA protocols such as DNP3, IEC104, Modbus, IEC6950 is always an option for utilities to connect with these DER assets with SCADA. However, there are a lot of drawbacks in this architecture. For example, DER assets are owned by third parties like prosumers, consumers, or retailers. So utilities cannot directly control these assets similar to other devices which they own and operate. Utilities shall ask permission for the operation, and there are contractual attributes which needs to be respected before taking any action. Legacy protocols are not designed for this kind of interactions. Like, for example, the protocols which we seen earlier, like DNP3, 104, Modbus, System-NP, etc. And SCADA systems is also does not fit for the high number of scalability because of the large penetration of DER resources in the grid. And there's no standard data model. That's data model for coordination, control, settings of DER resources are not standardized in the legacy telemetry protocols, which will again lead to enormous engineering effort for integration. The DER devices are installed at customer premises with customers' internet or network, which may or may not have adequate bandwidth. So it is critical to use communication protocol which can be adopted easily for this environment. DER devices are purchased from retail markets, which is supplied, and these devices are not supplied to the utilities. So the settings which is maybe stored inside the devices are totally private, depending upon the manufacturers or the geography at which these devices are being distributed. So to overcome these challenges, there is an option called IEEE2030.5. So IEEE2030.5 is designed to address above issues. So this standard is designed to connect or integrate consumer devices with the utility using widely adopted IP or HTTPS web technologies on client-server architecture, where the client is at the field, which get connected to the server at the utility premises or DER site display units. So IEEE 30.5 can meet all the DER specific use cases like monitoring the status of the DER when the DER is started and when it is disconnected. But the energy metering or conceptions or generation of these DER plans, how to we can also handle customer engagements and information by communicating pricing information to the customer, or give the energy usage statuses to the customers, or even send a test message to the customer as well. And 2030.5 can also use for request actions like on demand or demand response to a thermostat, or demand response to a smart plug, which is connected to the load in the customer premises. I can also change the inverter settings or send controls to inverters or EV charge stations. And a DER can also give controls and settings, like for example, curves, volt-watt curves, frequency watt curves can be returned to the devices on demand, or can be on schedule with start time and durations. So there are a lot of new use cases which can be using the 30.5 for the DER application. And for DER, especially, is designed for multi-hierarchy communication. Like there could be consumers, and there could be aggregators in between, and there will be utilities on top. So utility to DER aggregator communication can be done on 30.5, whereas utility to directly to the end devices communication, like the smart inverters or recharging network near prosumers, can also be directly connected over 30.5. And the communication profile is support a range of backward technologies, including wired and wireless internet, cellular, or any other media supporting IP. So thereby it is firewall friendly, which makes the integration easy with a few steps. On security standpoint, protocol ensures security through TLS, which is proven technology in web-based secure transactions. And it's also been easily adopted on any standard off-the-shelf hardware available on the market, or can be deployed on resource-constrained or battery-powered devices as well. It also has the ability to group devices and issue the settings or group commands to the multiple devices in a single shot. So these groups can be made flexible, like it could be based upon electrical network hierarchy or topology of the network, or it could be a customer engagements, like number of customers for a specific region, or number of customers above a specific segments, or it could be based upon the DR program. So these are flexible groups which you can create on top of this, and you can give controls and settings to multiple DRSS single shot. So IEEE2030 helps system operators to manage critical distributed energy resources like solar, wind, EV, and battery storage easily, unlike the conventional approach. Let's look at some of the functionalities which is provided by IEEE2030. These are the common resources and smart energy resources which is being provided. For example, in common resources, there's a time function which is used to synchronize the time by locating and acquiring time from a time source. It could be connected from a time satellite or any other time source. Common resource also contains the device information, like a static and specific information about the devices, power status information regarding the device current power source, as well as basic status regarding any battery installed within the device. Network status, like device network IP layer details, potentially link layer and performance details are also being captured and sent across using network status functions. And there's log events, which is used for asynchronous logging of the asynchronously generated warnings or out of bounds conditions or unusual events triggered by the devices are stored in the log events functions. And there's a configuration function which is used to read or write to the device operation configuration. This resource can be queried to provide current device configurations, perform configuration backup as well. And there's a file download and upload function set, which is primarily used for secure or interoperable remote software download to 30.5 devices. This function set may also be used for remote download of any other file artifacts, such as log files or configuration files or security credentials, etc. So these are a few set of common resources which is available as part of the 30.5 standard. Now let's look at the smart energy resources, which is provided by 30.5. The DRLC, that is demand response and load control function set, which is used by utility to control any client devices loads on real time, or it could be on scheduled basis as well. And there's a metering function set, there's a pricing function set, by basically tariff structures which is initially communicated by the utility to the HDR assets can be sent across using the pricing function set. It supports multiple tariffs, including flat rate pricing, TOU rate, tires, consumption blocks, hourly, day ahead pricing, real-time pricing, or maybe a combination of any of these can be supported. The pricing functions. Messaging is, as we discussed in the earlier slides, utility can also send a bad test message to the consumers or prosumers to inform them on view of the demand response program. So it could be any generation curtailments, so load curtailments or generation peak demands can also be sent across using the message function. Billing is provides the interfaces to provide the consumption or the cost of the energy. Also provides the estimates of the future consumption or historical consumption from service provider to an end device and provided by the billing system. And there's a flow reservation, which is primarily used for reserve the charge or discharge cycle, especially used for the plug-in electrical vehicles or the, energy storage devices with, or other managed loads that draw large amount of power. So that's the functions set used for the flow reservations. And distributed energy resource function set, which is primarily manages all the distributed energy resources, DER assets, like getting the status information from the DER or availability, capability of the do some DER controls like setting the DER curves to the devices, DER programs to the devices. All these actions and read operations are done through the DER function set. And there is a metering mirror function set. It's used for constant devices to post metering data to a metering server in an efficient manner. This is a prepayment function set. Defines the mechanism for a conditionally delivery of the services based upon the outstanding credit debit. And all these models are aligned with other standards like SunSpec, IEEE 1547, IEC 61815-7, etc. And we can also have manifest-specific proprietary extension for the function set as well, which give us the flexibility to add more features and functionalities into the existing standard. Now let's look at the adoption of the standard. So IEEE 2030.5 is the default protocol of IEEE 47.1, which is mandated for all the smart inverters to be supplied in the market. And California Rule 21, that is Common Smart Inverter Profile, CSIP, has standardized IEEE 2030.5 and mandated from 2020. And it covers all the use cases like direct DER communication from the DER access to directly to the utilities, or DER with embedded or separate smart inverter control. Should also support the 30.5 standard, or even there are generative facilities, EMS, which is managed multiple DER assets. So EMS should be able to interface with utility through 30.5. It can also supports the aggregator mediated communication, like all the DERs is being connected with the aggregator servers sitting in a cloud or on-premise servers, and from the aggregator there could be a direct connectivity to the utility servers on a direct B2B VPN connection. Apart from California, Hawaii has also adopted the standards through Rule 14H. AMO Australia is also adopting the standard in Australia. And there are a few enhancements to the California Rule 21 using 2030.5, working on using the standard for the vehicle to get bi-directional charging and discharging of the vehicles. Is controlled and managed by 2030.5. And it's also used for storage system management. Like it could be a fixed battery, or it could be mobile EV battery charge storage systems. It's been controlled and managed using IEEE 2030.5. Okay, so now look at the utility to multi-site DER integration options available. So in bottom you can see there are multiple types of DER, like utility vehicles, community solar, PVs or wind farms, combined heat and power generation units, battery storage units, rooftop solar, demand response, or microaggregator. There are multiple types of VR assets out there which needs to be integrated with system operators and the utilities, which is having a IEEE 2030. There are primarily two ways of integration, either directly from the DRSs to the system operators through a gateway, or it can be also through an aggregator. There's a retailer sitting in between and managing all these DRSs. All the data can go through the aggregator or retailer servers, and from there could be a 2030.5 connection to the utility system operator network. So these are the two types of integration options for a DRSS with the utilities. Now look at the solutions which is provided by Calculator. So for the gateway, which supports different protocols to communicate with DRSS like on DNP3, Modbus, Sunspec, Systematic, 101, 103, etc. This product called Calculator Edge, which is used for these applications. Let's look at the how it is connected. So Calculator Edge is a software which can be installed on Edge gateways, and Edge gateway can directly connect with different types of VRs on protocols like DNP3, Sunspec, Modbus, or System950, etc. And we can connect directly with energy meters or the inverters or serial or IP interfaces. We can also connect with the energy storage systems or the EV charging systems directly on REST or the on Modbus or different other proprietary communication links. For the DRLC, demand response and load control can be done through a thread devices, which is used to connect with the gateway, and the thread will in turn connect with the appliances, the consumers, and control these devices directly. And in cases if there's multiple DRs is connected to the EMS system, so EMS system can be directly connected to the gateway, and from the gateway data can give to the utilities on 2030.5 as an aggregator mode. And the data coming to the utility will be collected by the DR head end, which in turn will be giving to multiple applications like SCADA or ADMS applications, or could be a virtual power plant application, or could be a DMS applications provided by utilities. And this interface from the head-end system to these applications, legacy OT application can be on the legacy protocols like DNP3 or SYN, 104, STAPS, etc. And the gateways can be managed from a remote management server, which is Calculator.io, which will also provides the options to access these remote devices over a secure role-based access control using PKI infrastructure. And there's a PKI infrastructure which is also used for managing the connections to the utilities, as well as managing the connection with the remote management servers as well. So this is how the gateway-based integration works. On the aggregator-based solutions, so in aggregator-based solutions, all the DRSS are being connected with the aggregator, which aggregator software can sit on cloud or can be sit on aggregator on-premise servers. And from the aggregator servers, all the DRSS can be connected directly over the legacy protocols like DNP3, Modbus, Sunspec, etc. And aggregator, which is Calculator.io service, can integrate with the utility system on IEEE 2030.5 over a wired internet or a VPN network. Let's look at the solution details here. So here you can see that there are three stakeholders: utilities, retailers, or DR consumer or prosumers, and there could be multiple types of multiple DR customers. Customers having multiple sites, which is connected to the DR data hub, DR aggregator, through the customer's VPN, and this customer VPN will be isolated through a virtual gateway appliance, and the virtual gateway appliance will communicate with the DR assets on different protocols like TNP3, Transmit Modbus, 3.5, Snap3 Modbus, or any customer proprietary protocol through the customer dedicated VPN, or it could be custom internet with the TLS 1.3 tunnel with the aggregator server. Like that, there could be multiple customers which is connected with the DR aggregator through its own virtual gateway appliances, which isolates the public communication through a public internet with the DR access. And from the DR aggregator, data can go to multiple system operators. So the energy supply can be provided by a single utility or could be multiple utilities. So depending upon the use cases, Calceo aggregator can give data to single DR headend or multiple DR headend from the different sites. So it's a selective mapping option where you can select which all sites should go to which all operators. And it's a multi-tenant architecture which also manages the multiple accounts and data is being isolated from each accounts separately. And there are two deployment options for DR aggregator. It could be on hosted service, or it could be a software which can be installed on the retailer's network or retailer server as well. And from the retail network, there will be a B2B VPN link from the aggregator server to the utility data center or DR headend, which will send data over 2030.5 standard. So these are the 4 different products which is provided by Calcitech. DR gateway software, that's Calki.io 2300, which is a software-based solution which can be installed on any standard hardware. DR gateway hardware, which is Sync 2310, which is also called as the remote-side gateway, which has been approved by a few utilities and is used for integrating the DRSS with the utility servers. The aggregator, there are 2 options. There's a DR aggregator software. This is software which can be installed on the retailer infrastructure. And there is an option for the aggregator hosted services, a multi-tenant service, which can be subscribed on demand basis. So depending upon the number of DRSS which has been hosted, there will be a subscription model available for the hosted service, where you can connect the DRSS, and from the DR aggregator you can link directly with the utilities DR header. Look at the details of the gateway models. So this is the hardware model, that is Sync 2310 hardware, which comes with Intel Atom processor with 2 Ethernet to connect with the field and other devices, and there are 2 serial ports which comes with 232 or 485 ports, which can also directly connect with the DR assets in the field. There are few USB interfaces, and the device is fully hardened, combines with the hardened Linux with the TPM 2.0 secure boot and inbuilt firewall, which enables to with the high security devices for the exposing data from a DR site. And it's NEMA 4 enclosure polycarbonate which can be mounted on a wall, and it can meet minus 20 to 70 degrees Celsius on rugged environment. And it also have inbuilt modem. This is 4G modem. For the US, there's a modem is combined to FirstNet to connect with the utilities private leased line network. On the software, the KIO 2300, which is a software which is primarily available on Debian or RPM or Docker packages, can be installed on standard hardware like x86 or x64 with 1 GB and 500 MB storage. It's also available on specific platforms on ARM or PowerPC, starting from 32 MB RAM and 14 MB flash. It's available on request. So there are a few hardwares which is also validated with these configurations like AdLink, AO, Vendec, RAD, Raspberry Pi, Phoenix, IEEE, and few ODM's hardware are also validated with the IEEE2030 software. About the connectivity interface with the field or to the southbound as well as northbound. These are the utility connectivity interfaces. Like you can also connect on System 950, DNP3, 60870, 104. DLMS version for connecting with the metering head and systems. ICCP to connect with the that is intercontrol center protocol to connect with the SCADA systems or EMS systems. 614.0025 to connect with the wind farm plans. 30.5 for the other DRSs. For the DR connectivity, as per IEEE 1547, DR should meet any of these protocols. That 30.5 is the default, and or it could also have Sunspec Modbus or DNP3. So all these interfaces are supported in the edge or the aggregator software, and it could also connect on Modbus, standard Modbus or System 915.7 BACnet or 104, which is all these protocols are supported in the edge or the aggregator as well. And from the gateway or the aggregator, you can also give data to the other IoT platforms like Amazon, AWS, or Microsoft Azure. There are a few services which has been provided by Turkey.io to connect with IoT, AWS IoT Core, AWS IoT Sitewise, AWS Kinesis as well. And to Azure, you can also integrate with the Azure IoT Hub and create a device tuning service in the IoT Hub. And for the other industrial IoT platforms, data can be exposed on OPC UA standard or MQTT, WebSocket, AMQP, or lightweight MQM protocols. And we also support few NMS or time signature protocols for the network management and time management options. So these are the interfaces for the southbound and northbound from the aggregator and the gateway product line. And 2030.5 is been certified by Sunspec as per the CSIP version 2.1, and all the aggregator and the gateway products are being certified for the CSIP file, which is mandatory in the Sunspec CSIP government. So on the security side, we have the multi-stakeholder trust chain support. Multi-stakeholder trust chain is used for securing the device and securing the communications for multiple use cases. For example, there's three types of PKI infrastructure which is supported. PKI 1 is trust chain 1, which is provided by the manufacturer ASE or Telgitech, which is used for signing the firmware and the configuration files or patches, security patches for the devices. So only the firmware which is signed by the manufacturer can be downloaded into the devices, which ensures that no other malware or any other third-party softwares can be installed on the hardened devices. And there's a option for TC2, so trust chain 2, which is primarily used for device management and the remote access. So this is private PKI infrastructure which is managed and maintained by the O&M, or can be managed by the utilities as directly. Utilities can create users and roles and give permissions for different set of devices to different set of user groups with a different set of permissions. And all this permission management is been done through X509 certificates. Fine-grained roles and permission can be managed using OCSP, that is online certificate status protocols, all through an attribute certificate, which is based upon 62351-8 RBSC standard. And it also supports the trust chain 3, which is PKI for the end user communication, which for in this case 2030.5 connection from the aggregator or the gateway to the utilities can be secured through the TC3, and certificate can be provided by the PKI infrastructure, which is managed by the system operator or could be managed by third party. Like for example, Sunspec PKI infrastructure is managed by third party, and we can get these certificates and use the certificate to connect with the utilities directly as well. So these are the three types of PKI infrastructure which is supported by the gateway or the aggregator. Let's look at this example of the PKI infrastructure for the California Route 21. That California Route 21, as I mentioned in the earlier slide, is being managed by Route 21 CA. It's a third-party entity which is provides certificates for each 2030.5 aggregator or to the gateway. And this certificate is used to establish a secured connection, TLS connection from the aggregator or gateway to the utility server. And you can also use utilities on private PKI to connect with the DRSS with the aggregate as well. So this is an option which can be enabled or on request to establish the secure connection on the downstream. So let's look at the few case studies which the solution is used. This project in US which is used for integration of DR sites with a capacity of 3 megawatt or higher with the utility as per rules California Route 21 mandate. So the hardware product IC3235 is used with the calculated software in it, and it's used to connect with the DRSS like meters or inverters or EMS systems on different protocols like Sunspec Modbus, standard Modbus system FT or DNP3. And from data collected from these devices is been sent to the utilities, their head end through 2030.5 protocol. And the gateways as well as the remote devices can be managed and accessed through the CalCAU device management and remote access service, which is also based. It's also hosted on the cloud. So this is one of the case study which is deployed with the gateway hardware. Another case study is in New Zealand, where we calculate software IEEE2030 is being used on a third-party hardware, third-party edge device, where the requirement is to optimize the distribution network usage and avoid capex spending to address the penetration of EV and solar, combined with demand response to load control customer loads. So this is the use case, and KA23008 is being used to connect with the inverters on the Sunspec Modbus, EV charging station on standard Modbus or REST APIs, depending upon the EV chargers which is being connected. And the customer loads is being controlled through a thread devices, which is combined to a standard Australia standard AS4755.3.1. And this has been controlled from this data has been consolidated, aggregated at the gateway, and this has been sent to the DERM systems, which is hosted on the Azure platform on 2030.5, and the gateway management and remote access is been done through the Calculator.io remote device management and remote access tool. Here in this solution, the load control is being managed through the standard called that is the demand response program is managed through the program called AS4755.3.1, which is a standard in defined for Australia and New Zealand market. And the appliances are compliant to Australia. This standard will support primarily three commands like DRM1, DRM2, and DRM3. DRM1 can completely shut down the device from the load. DRM2 can switch the load to 50% of the capacity of this particular equipment. DRM3 command can switch load to a 75% capacity, and there's a command called DRM4 which switch load to a 100% capacity as well. So the 4 types of commands are supported by the any of the equipments is compliant to the standard, and these devices can be directly integrated with the gateway through their thread standard, and from the gateway you can control from the DEMS applications or from the utility SCADA applications. So these are the 2 use case studies, and we can wind up to making the benefits for the stakeholders. For utilities, this 2030.5 solution is used to improve the grid stability without impacting the penetration of the renewables. It's also used for managing non-essential loads for curtailment during the peak demand. Also used for regulating the EV charging stations during the peak demand period. For the DR owners or prosumers, the solution is used to increase the ROI by improving the generation yield for a DR generator stations. It is also used to increase asset life by proactive maintenance and reduce the operating and maintenance cost, and also complying to regulations like, for example, California 21 or other standards which is coming in the regional market. For the retailer aggregator, the seamless integration with the system operators, DEMS or ADMS applications ensured using the standard or using the solution. Also, retail will also have increased retail customer base. More and more customers can directly connect with their systems on a proprietary or any standard protocols, regardless of these protocols. And utility interface will always be standard using the 2030.5. And also increases the enabled market penetration for the retailer segments. And for OEMs or the inverter manufacturers are using the solution for improving the equipment life by monitoring and of operational and performance data and take necessary actions on time. And also secure role-based remote access solution provided by Calculate.io is used to avoid the site visit and travel. For any use cases like updation of the firmware, updation of the softwares, configurations, or doing some troubleshootings, all these remote device access can be done remotely, as if user is doing it locally on the DR devices on the field. So with this, I would like to conclude my session. So a few references which I have used, and if there is any questions you have, please feel free to send us to marketing@calculate.com, or can type in your questions on the GoToWebinar questions box. We will get back to you as soon as possible. So thank you all for your time and to attend this webinar.